Okay, hello everyone. So in this video we are introducing the Laplace transform, which is really one of the fundamental concepts in our introduction to differential equations. So before jumping into details, let's try to understand from a bird's eye view what value this idea is going to have for us. Well, our general problem is that we're looking to solve differential equations. And this is really how the Laplace transform is going to help us, because for a given differential equation, we'll be able to transform it into an algebraic equation using the Laplace transform. And then with that algebraic equation, we can freely use our algebraic techniques to manipulate it to get a specific form. And then once we're there, we can apply what's called the inverse Laplace transform to derive a solution to our original differential equations. And that's really the three-step procedure here that's going to help us solve differential equations. So in general, the Laplace transform for us is just going to help us solve differential equations. Okay, so let's see some of the details. Well, firstly, the Laplace transform is completely defined here in this box. And so we can already see some things. The first thing is that the Laplace transform, it's a concept which applies to a function. So it's like it takes as input a function defined on a specific interval, and it creates from that data another function, which is on the right-hand side here. And this function here is a function of another variable, not t. It's a function of a variable s, and that's the important thing to see. So from a function of a variable t, defined on this interval here, we are creating a new function from it. And that function can be defined on a different interval, by the way. It need not be defined on interval 0 to infinity. Okay, so let's familiarize ourselves with this topic with two examples. So we're asked here to compute the Laplace transform of this specific function. So f of t is equal to e to the t here. And to do that, let's just go right ahead and compute what the, from first principles, what is this integral. So we have to compute this integral from 0 to infinity of e to the negative st times f of t dt, and f of t is equal to e to the t here. So we just have this. And here you can just see that this is the same thing as this. And we can already integrate this and get it into this form. So here we'll just have 1 over 1 minus s times e to the t1 minus s, and that's it, from 0 to infinity. So our bounds here are still 0 to infinity. So how do we interpret these bounds? Okay, well, 0 is easy enough, but what do we do with infinity? Well, formally, what we have to do is make this equal to a limit. So we replace the infinity by a b, and then let b go to infinity. But we can skip those steps and just make some simplifying arguments. Okay, so the first thing is to see is what happens with s here. So if I had to plug in a number, a very, very large number here, so I take, let's say this was a b now, and I know that b is very large, and I plug it in here. It's going to depend. I mean, what will I get is the question. Well, it depends on what s is. If s, for instance, let's just argue here. If s is, let's say less than or equal to 1, okay? Firstly, if it's equal to 1, this here at the bottom is not going to be defined. So, okay, this is not defined at all. So s can't be equal to 1. At least we know that now. Okay, but what if s is less than 1? Well, then this number here is positive. And then as we plug in a big number into an exponential function, we're going to get a really big number. So the point is that if s is less than 1, then because this exponent here is going to be positive, and then because the exponent goes to infinity, this whole expression will go straight to infinity. Okay, and so for s is equal to 1, the Laplace transform is actually going to be undefined. Okay, so the only thing to check is what happens when s is bigger than 1. So in this case, s bigger than 1, we can then get an exact formula. And that formula is going to be easy to calculate, because if I take if s is bigger than 1, then this number here is going to be negative. And since t goes to infinity, this is going to be an increasingly large negative number. So this number will go to negative infinity. T times 1 minus s will go to negative infinity. And so that means as this goes to negative infinity, this here goes to 0. This part here goes to 0. And so the whole expression goes to 0 for this bound. So the whole point of saying that is that when I evaluate this, I'm going to get 0 minus, and then I just plug in 0. So 1 minus s times e to the 0 times 1 minus s. And here, this will just be nothing other than just 1 over s minus 1. So the nice thing is that here, the Laplace transform is going to be exactly equal to 1 over s minus 1. Okay. So I'll just store that information in this little statement here. S must be bigger than 1. Okay, good. So you can immediately see something here. And that is, so the first thing to see is that we really only care about the part where the Laplace transform is defined. And so we actually only write that here. So the Laplace transform of f in this case is just going to be equal to this. And we just keep in the back of our minds that s must be bigger than 1. Okay, in general, what about different exponential functions? Well, the nice thing is that we can have a formula, and that's what this formula up here is saying. We want to compute the Laplace transform of e to the alpha t, then it's just given simply by this formula here, and then I leave it to you to calculate what is the bound here. So s should be bigger than something, or less than something. Okay, let's look at another example. So we want to now compute another Laplace transform. So here our function is just equal to t, so f of t is equal to t here. So we know what this integral is. It's the integral from 0 to infinity e to the negative s t times t dt. And how do we integrate such things? Well, this is going to require a bit of technique. We have to remember a formula, and that formula is integration by parts. And the formula for integration by parts will just tell us that if I want to take the integral of for instance, u prime v dt. This is the same thing as just u v minus the integral of u v prime dt. Okay? So this integration by parts, the real thing that we need to do is decide what is u prime and what is v, and then compute what is u and what is v prime. So we want to get rid of the t. And so that's what we're going to choose our v to be, because we know if we differentiate v when it's equal to t, then we just get 1. So that's how we'll get rid of it. And so u prime here is just going to be the other function, which is e to the negative st. And so here we immediately get what is u and what is v. So u is just going to be equal to negative 1 over s e to the negative st. And then, of course, v prime is just equal to 1. Okay, great. So then, from integration by parts, we can write this as simply u times v. So we have u times v here. So we're just going to get negative t over s e to the negative st. That's just the u times v. Minus the integral of u v prime, which is just e to the negative s, the negative s here, negative st, times v prime, which is 1, times dt. Okay, great. So here I can remove the sorry, and I said u. This is not what u is, my mistake. U is negative 1 over s e to the negative st, my mistake, times v prime, which is 1. So here we're going to have dt, just like this. Okay. Great. So all of this, by the way, is contained within our bounds. So we have to put in the bounds here. And this will go from 0 to infinity. And so let's simplify this. Simplifying this, we just get negative t over s, same thing. Nothing changes with this term. And now we're going to integrate this. Now we have negative, negative, so this becomes actually positive integral 1 over s e to the negative s dt. But now when we integrate that, we're just going to get negative 1 over s squared e to the negative st. Okay, great. So we get here again, the bounds go from 0 to infinity. Okay, great. Now we're going to make similar line of arguing as we did earlier. We have to kind of condition on what happens with s. If s is less than something or bigger than something, some conditions we're going to be able to. This is either going to be defined or undefined if s is bigger or less than something. So the first thing to see here is that s can't be 0. Why? Just because there's denominators which contain only s. So s can't be 0, that's fine. Now we ask the question, can s be positive? Is s allowed to be a positive number? And the answer is yes, because if s is positive, then negative s is negative, and s can go to infinity, which will kill this term here. It'll make it 0, and it'll make it 0 here. Can s be negative? Well, let's say s is negative 1, for instance. Then we have negative 1, negative 1, which will make this s here positive. And then as t goes to infinity, this term goes to infinity. And so it'll be undefined. Okay. So again, we are getting to the conclusion here that s actually has to be bigger than 0. And that's when our Laplace transform is going to be defined for. Okay. So supposing that s is bigger than 0, let's argue what happens. Well, all of these terms are actually going to go to infinity. 0, sorry. So it's a bit tricky to see, but if I have to take the limit as t goes to infinity of negative ts e to the negative st, you can use many ways to see what this is going to be. So for instance, this can be rewritten as a limit as t goes to infinity of negative t over s e to the negative st. And in this form, you can use L'Hopital's rule and just quickly see that this is actually going to go to 0. The point is that this limit actually goes to 0. Sorry, this shouldn't be negative here. It should be just positive. Okay. So the point is, as t goes to infinity here, this expression goes to 0, and so does this one. And so, again, we're going to, when we have to evaluate what this is, we're going to have 0, and we're going to subtract from that. Now I plug in 0 wherever I see a t. Now this 0 being in front here, being in the as this coefficient here, is just going to kill this term. So we're going to have 0 minus, and now when I plug in 0 here I'll just have 1 over s squared times e to the negative s times 0, which is just e to the 0, which is 1. So I'm just getting minus 1. Negative 1 over s squared. And this all turns out to be equal to 1 over s squared. Okay, great. So the Laplace transform of this function t, f of t equal to t, is just equal to 1 over s squared, and s must be strictly bigger than 0. Okay, again, as earlier, this actually has a more general form, and that's what's given up here. And so I encourage you to go ahead and see if you can prove this formula. It's not completely trivial, but you can. We will get to this eventually in a future video. But if you want to give it a shot, it's quite fun to do it. Okay, one last thing is that this is really one of the main reasons for using the Laplace transform is because once we've calculated the Laplace transform of some functions, we don't have to do it again. We have the basic. Once we've computed the transforms, they're there forever, and we never have to do it again. And that's really one of the things that makes this a valuable technique, this Laplace transform technique, because we can tabulate. We can have a systematic approach to using the Laplace transform, because we can, once we have these, for instance, we can use them in what follows. Okay, and so here this table just gives you some of the basic Laplace transform. So we've already seen what happens in the case, for instance, n equal to 1 was the previous situation, and here we'll just get 1 factorial over s to the n plus 1, which is n squared, and this is just what we got, 1 over s squared. And here e to the alpha t we already saw is equal to this, but then also there's generalizations. T to the n times e to the alpha t is given by this formula, and so on and so forth. So in the future, we will see how to actually get to these formulas. But anyways, I think that's it for this video. Thank you.